So it's a pleasure to introduce José Blanchett. He is at Stanford University in Management Science and Engineering. Before Stanford, he was with the Department of Statistics and IUR at Columbia. And before that, he was with Harvard in the Department of Statistics. And he is generally interested in applied probability, computational finance, MCMC, queuing theory, rare event analysis, risk. He is a recipient of a number of awards, including 2009 Best Publication Award and the Informs Applied Probability, and 2010 Erlang Prize. He also received the Stochastic Award from NSF in 2010. And today he will talk about statistics of Wasserstein distributionally robust optimization. Please take it away.
Thank you very much, Sasha, and thanks very much for the kind invitation. It's the second time I give a seminar at MIT, and to be honest, it's also I always enjoy a lot. The first time it was when I was at Harvard, so it already has been over 12 years, I think, and so thanks so much. It's always very special. I wish I could be there in person. My guess is that there are a number of you and at MIT with whom I would love to talk in person about this. I consider myself a bit of a newcomer to the area of distributionally robust optimization. The first papers we wrote about the topic they were in 2016. It looks like in this very fast-paced research time, it looks like ages. But for me, there are still many things that I am learning. So being in person and talking to many of you, I think would be great. Hopefully, this online format might be even more conducive to potential future interactions, which I would welcome. Anyway, so this is a joint work with Yang Kang, who is a former student of mine, who is now at the show, Karthik Murthy, who is a professor at Singapore University of Technology and Design, and Nian Si, who is one of my PhD students, and this is based on 2 papers. So I'm going to discuss first the first slides. Before I tell you what are the results, I'm going to talk about what is the object of a study. What is this talk about? And for many of you, being MIT and knowing the activity, the high level of activity that is there in robust optimization and distributionally robust optimization, this perhaps might be a little redundant, but I think this is not mainstream. Still, I think is becoming very popular, so it's worth kind of like at least sharing my perspective. I think about why, what is it? How do I interpret things? Why do I care about that? And before I actually talk about the mathematics. So a data-driven distributionally robust optimization takes form like this. I'm going to highlight the elements of this formulation, right? So there is a loss function. This loss function could come from the likelihood principle, could be the quadratic loss. It's typically chosen by the statistician in a way that is more or less standard. There is a decision parameter that we're going to be using as notation throughout the rest of the talk. That you see this PN here, that's the empirical measure. I'm going to be assuming data to be IID, but towards the end of the talk, you're going to see that really what is in place is just an assumption that allows to carry a central limit theorem with some uniform integrability condition. So, but let's keep it. The standard approach is, the standard assumption IID. There is the more interesting part that is different from the standard kind of empirical risk minimization formulation is the sauce, right? So this is the uncertainty region. So this is U for uncertainty region, and there is this parameter that is quite crucial, which is the size of uncertainty. Now there is also the geometry. So this is the size of the radius, and there is also the geometry, which I'm going to be parameterizing in terms of a distance, and this is where the Wasserstein distance come into play. So this D is going to be the Wasserstein distance. This formulation is what is understood as the distributionally robust optimization formulation. The Wasserstein distance is so flexible that by choosing the transportation cost function, as I'm going to explain in a minute, in the right way, you can get rid of this probability and just have a set here of outcomes, and in which case you would recover robust optimization. So these two notions are actually very, very related. So this is the formulation, and I'm going to explain, why do I care about it? What does it model, etc. Obviously, it's very intuitive at the moment that what you are doing is you're trying to find an estimator that performs in the best possible way as against an adversary that somehow is going to perturb the probabilistic model. And a lot of the questions that I consider most interesting and open have to do with how to choose this thing. This talk is not about that, but is going to shed some light into that, but we are not right there. And also how to choose this optimally. And I will provide an answer to that question here, at least one sensible answer. Not the only one, but I'm going to give you an optimization criterion that this is going to satisfy, and I'm going to solve that optimization problem. And the optimization criterion is very, very statistical. All right. So as I said, this connects to a very large body of literature, to robust optimization. You can change the notion of distance to something more, divergence, the divergence notion, for example, and in which case, you have a different type of geometry. There are advantages and disadvantages. I could talk about that, and I can answer questions, but I don't want to. I have very limited time. And then this is closer. This Wasserstein DRO is closer to uncertainty regions that are derived in terms of moments. Those are the ones that I think you can trace back to the late 50s with the work of Scarf. So it is not new. It has been around for a long time. But papers that have to do with this, with Wasserstein DRO, there was work of Peter Hoover that sort of was using like one-dimensional versions of the problem. The work of Floch and Wasserstein also involving like one dimension. And then in around 2015, 2016, Dan Kuhn and the oil group and Rui Gao and Antoine Clivewaite, we were working independently on these problems. I was working more on the side of applied probability, not really machine learning. But then, we kind of like intersected, found this connection. So these types of problems really using Wasserstein DRO in the context of high dimensional process. This talk is going to fix the dimension, but I can answer questions about more high dimensional results. Is really relatively new. And then there is this work of John and Hong that connects this type of representational problems to the context of adversarial training of neural networks. So it connects to several interesting areas. Now, I told you that D was going to be the Wasserstein distance, so I'm going to explain what the Wasserstein distance is very quickly. The Wasserstein distance is the cheapest way in which you can transport mass from one distribution, right, to another distribution. I think of it as kind of like transporting mass from like a pipe of sand and sending it to a sinkhole to cover the sinkhole. So this corresponds to Q, this corresponds to P, and there is a cost of transportation per unit of mass that is C of XY. So this C, throughout the rest of the talk, I'm going to refer to that as the cost, and the L is the loss, right? So the L is the loss, this one. Okay, so you need to remember this so far, like the parameters. Beta is the decision parameter, C is the transportation cost in the game, L is the loss, and the D is the distance. Okay, so there is a book by Cedric Villani, 2003. This is a book where you can have, it's a great introduction to optimal transport. It will talk about everything about this linear programming problem, its dual, etc. So what we are going to be, when you specialize the cost function to be a metric, right? Any kind of metric, in particular, for example, one that arises from a norm in RD, then you recover the Wasserstein distance. And what I'm going to consider in this talk is the Wasserstein distance, the type 2 Wasserstein distance. In fact, many of the results that I'm going to discuss work with something of this form. As you'll see the sketch of the proofs towards the end of the talk, you will realize, and some of them actually with R equal to 1. The R equal to 1 is a bit of an annoyance, because you get discontinuities in limits, and you cannot use necessarily plug-in estimators to compute the different quantities that you need, but you have their characterizations of what the limits are. But so for a talk, like a 50-minute talk, I think it's convenient to just keep the calculation simple and just concentrate on the Wasserstein 2 distance. In this case, then when you choose this as your cost function, the norm square, then the distance is this. Okay, you need to take the square root. All right. Okay, so the Wasserstein distance is used a lot, not only in statistics, in image analysis, for example. There's I like this picture, like there are in artificial intelligence, the Wasserstein GAN, but in image analysis, comparing or deforming images using this technique, is very common. I gave you a picture of the Wasserstein distance that look static, transforming some distribution. In this case, could be the uniform distribution and the support of this armadillo into the uniform distribution in a ball. And I gave you the static picture, but turns out that actually you can embed it in a dynamic way, and you get pictures that are smoothly sort of deforming in a very, very natural way. Okay, so there are, if I had time, I could also tell you how that can be described also parametrically in the uncertainty size, like the worst case distributions as well. There is a dynamic effect, but I'm not going to have time to talk about that. But this gives you a sense of how is used the Wasserstein distance, how widely used is. So why do I care about these types of formulations? Well, to me, they are a very natural way to deal with out of sample impact. So turns out that this LP formulation, you can also relax it a little bit in these types of problems if you have enough convexity, or not necessarily convexity in the parameter space X, but if you have if delta is small enough, and delta will be small enough in this talk, but naturally you can relax it to something that is literally out of sample. So you have a budget of size delta, you have a transportation cost of perturbing the data, and this uncertainty region is basically saying, you are going to perturb each data point any way you want, in such a way that the total budget, as measured by this, is less than delta. Okay, so that's kind of like what this thing is doing in the end, and it's very intuitive. So you have literally, you are embedding the out of sample problem like this. So the Wasserstein DRO estimator, doing this optimization, by the way, wouldn't be convex. This is related to kind of like what is known as the Munch problem, but the formulation relaxes it and gets asymptotically this, and this is in a way kind of relaxing this sort of intractable problem. The Wasserstein DRO estimator is just the best response when you perturb delta. So also, the cost function can encode side deformation. Again, I don't have time, but in this paper, what we do is we solve an optimization problem, like an application in finance, where we use the Wasserstein this cost function to encode, for example, implied volatility. So we can encode, for example, the size of the perturbation using the implied volatility, which is not a statistical information, but prospective information from the market. So if you want to endow your estimator with good sample, out of sample properties, what you want to do is, you want to make this cost function, you want to make this perturbation to be cheap, easy to move, encourage movement. If you know that excise, for example, land in a region for which you don't have a lot of information, then you want to explore more. You want to make it cheap for the transporter to move points around. If you have regions that carry a lot of information, maybe you don't want to send, you want to make it expensive. You want the artificial player to explore out of sample in a way that is beneficial. And so that's how we do that. We use implied volatility to inform that. So if the implied volatility is very high, then the cost is 1 over the volatility, so it's cheap and it can explore. If the implied volatility is very little, then 1 over the implied volatility is going to have a huge cost in that direction to move points, and that gives you an idea, right? So you can encode side information, and that's really what I like the most about this flexibility. Now, it also provides a way to do a statistical regularization. So this is a picture that shows 1,000 experiments of some linear regression problem in 2 dimensions, where you have a lot of collinearity, positive and negative collinearity in the 2 predictors, and we compare here the output of the estimation. So we have, I think, 100 points in the linear regression. We run the empirical risk minimization. I'm going to be calling ERM, empirical risk minimization. And each black point that you see here is an estimate of the true solution. The true solution is, in this case, this aqua point. And we have these 1,000 experiments. The red points correspond to the DRO estimators. And of course, using, I think, the L2 distance as the cost function with an optimal choice of delta, okay? And so you can see that happens is that you have a little bit of bias, but you have a lot less variance. Is this variance trade-off? And in the hard cases, let's put it that way, you regularize the problem and you have a much more concentrated sort of cloud of points than without the ERM estimator. So this is, the effect that some sort of regularization. In fact, the regularization can be made rigorous and explicit. You can recover square root lasso, support vector machines, group lasso, regularized logistic regression. Folks from Santa Barbara have applied it to graphical lasso in the context of Gaussian graphical models. There are many estimators that can be recovered. There is a very nice survey paper that's like a 90-page survey paper that talks about Wasserstein, the DRO, all of the properties, and summarizes many of these results. And so that's also kind of reassuring that you can connect to that. I also mentioned connections to training, adversarial training of neural network, the paper of John. So there are many different connections that have been established, and so it's flexible. It allows you to incorporate side information. You recover exactly. By the way, these are exact recoveries, not approximate recoveries of these estimators. You can do like a sanity check whether the results that you obtain from this theory match the high-dimensional statistics theory. They match. But you can do it for much more general or widely more formulations, right? And so that's why I care about this. And so once I have told you now what is it that what I'm going to study, what is this talk about, what is Wasserstein DRO, the connections, and why do I care about that, then now I can tell you what is this talk about, really truly about, right? So the talk is really about, how to choose this delta parameter optimally from a stats standpoint. And given this optimal choice, how do we do inference with this problem, right? So how do we kind of obtain asymptotic normality? And in my quest to answer these two questions, I'm going to introduce another object. So it's going to come in the next page, but it's a very special sort of like confidence region, which is going to help me guide this guy here. So the next part, so I'm going to answer these questions, but before I do that, I am going to introduce that. So it's going to sound like I'm going to do a detour, but it's because I am in my goal to answer this. That's kind of the hardest, to be honest. Once you have that, then this is kind of okay, technique, a fair amount of technique, but this is more modeling, a little bit more modeling. Okay. So as I say, let's assume that the data is IID. Let's select delta. So there are two options, and these were the options that were like if you look at everything before, like this 2016 paper that we wrote, I think in the area, or most of it, I don't know, like everything I remember seeing, but maybe and even the books of Hansen and Jansen, like in economics, in the context of the entropy. The one choice, that sounds appealing and natural at first is choose delta such that the true generating distribution is in the region with high probability. And the problem with this choice is that is not informed by the loss, you see. And that should give you pause, because that means that you are kind of robustifying against every possible, for every possible case or every possible use case. And that has to, lead to too conservative estimates. And that indeed happens, right? I mean, if you do this, then you are typically going to end up with choice of delta that is going to scale very poorly with the dimension. So we want to avoid that. That's turns out not to be a good idea, even though still many papers kind of like, that's how they guide the choice of delta. It's just not really workable. Another approach is the following. What you can do is you can say, well, I'm going to take this set, the uncertainty set, and I'm going to project it, but into the space of optimal decisions. That's one thing that you can do. The other thing that you can do is you can say, well, I'm going to pick delta in such a way that I enforce a generalization bound on my objective function. So that is fine. Both things are perfectly fine. But in this talk, I'm interested in the decision, in the optimal decision. I want confidence regions, and I want a fluctuation theory around that. And anyway, if I can obtain a result, a good coverage result for the decision, that will imply a coverage result for the value function. So this is harder and it's more interesting for what I want to talk about. In both cases, it's okay. You can project either to the space of decisions, so you can project to the space of generated optimal values. That's fine. So I'm going to choose this thing, projecting into the space of optimal decisions. Now, what does that mean? Well, this is what I mean. What I'm going to do is I'm going to take every possible member of the uncertainty side, and I'm going to compute the optimal decision for each of those members, right? So if these members, if delta is well chosen, these members are reasonable perturbations that I want to explore out of sample from my model, including side information and so on and so forth, right? And then, therefore, each of these solutions are reasonable decisions that I could make for my parameter beta. So this object here is the natural, projection of this space, right, into the decision space. So it's the projection of the uncertainty region into the optimal decision space. So this object is now can be interpreted, if you will, as a confidence region. Now is a finite dimensional confidence region, and then I have a much more hope to have a choice of delta that scales nicely and is not affected by the course of dimensionality, right? So what happens is that this object is increasing as a function of delta. So, kind of start thinking about an optimization problem that I can postulate that, ends up having a target coverage probability that I have. And that's the option I'm going to pursue, this confidence region. So I'm going to be interested in analyzing this confidence region jointly with the DRO estimator, right? This confidence region is going to tell me how to choose delta optimally. Again, because this is increasing is in delta. So there is a notion of minimality, right? Subject to the constraint of the coverage. So this is going to tell me how to choose delta, and now I can talk about, convergence, if I want convergence, joint convergence of the ERM, the empirical risk minimization estimator, which is delta equal to 0. I can talk about this convergence jointly with this and jointly with this object, for example, right? Once delta is chosen optimal. Okay, so now I'm ready. I'm ready to deliver the result that I promised, like that I wanted to do, which is the fluctuation theory around this guy, an optimal way of choosing delta. And hey, why not? I mean, this guy there, I'm going to throw it in. So this is how it looks like. Okay, there is a lot of stuff to parse here, and so I'm going to go through it. So it says IID sample again. This is something that we can relax. You will see from the proof. You just need you will see that you need a central limit theorem operating. It says 3 times differentiable. It really is 2 times differentiable plus some local convex assumption on the second derivative. So basically it's 3 times differentiable. So this is a talk. I don't have time to list all the assumptions there, but this is a little bit more than what we need. And you need the gradient of this loss to be square integrable. You have a condition of non-degeneracy of the Hessian of the function of the optimizer, and in particular you have a unique optimizer here. So what the theorem says, well, I am going to choose delta n to be eta divided by n to the gamma, and I'm going to just parameterize gamma and let's see what happens, right? So so you have joint convergence to these 3 objects. We are going to so you have this limit loss can be characterized. I will do it later in the talk, as I'm going to kind of like peeling off this onion, right, of what this all means. You have this result that is very well known, standard. I mean, what happens with the empirical risk minimization estimator, that's the case when eta is equal to 0. That converges to some, you have Gaussian asymptotic normality under the assumptions I'm describing. And the converging to a distribution, right, with this covariance. This, as I said, can be computed explicitly. I think at this point, I want to maybe take a minute to ask a question to see if the notation here is clear. What you need to remember here as we move forward is this constant. This is eta is a constant to be chosen still, to be chosen as well as gamma. Okay. Gamma less, the smaller the gamma, the larger the delta, right? So if gamma is tiny, because you know, that would mean if gamma is 0, for example, delta is of order 1, right? So smaller, the delta shrinks. The delta shrinks as gamma increases.
So what is the point of analyzing gamma not equal to 1?
The point of analyzing gamma not equal to 1 is to come, well, gamma will end up being equal to 1. That's the optimal choice. But people, as I said, you know, people used to actually select, most of the papers were actually selecting delta like this. So, you know, after reading 20 papers of people selecting delta like this, maybe these people need help and they need to, you know, understand that there is actually a point to analyze gamma equal to 1, right? So I do it because so that, you know, so that I can show the optimality of delta. That's the reason. But if, you know, once you clearly already identify and know that gamma is equal to 1, so that's not going to be surprising to you. But the fact that gamma is equal to 1 is going to come from this analysis. It's going to come from here, that gamma has to be chosen equal to 1, and it's also going to come from here that eta, that the specific choice of eta, right? So that's why I'm doing it, kind of like to settle that question, basically. All right. So I'm going to, I am going to give this result later, but again, I cannot sort of start talking about that without knowing what eta is and what gamma is. Gamma is equal to 1, indeed. But, you know, we want to see, and I also need to tell you what eta is, right? And so that is going to come from this part here. So as I say, this object really represents a confidence region. And what I want is to have this optimizer beta star inside that confidence region with high probability. So that is going to be the same as demanding that this object here has 0 inside of it. And that is the same coverage question, happens if and only if. So I am interested in the, you know, checking whether this happens or not. So this is a set, and this is a point, a random point. So I'm moving that set, and this is a random set, right? And I want to see if this random set covers 0 or it doesn't cover 0. So what happens when gamma is less than 1, and then maybe this is a little bit of a point of what is going on. This confidence region turns out to be RD. So that means that you are being very pessimistic. So if you were to pick n to the power 1 over d, which is what is the tip, some, you know, it has been the canonical selection that most of the literature tried, right? Then that would give you like sure, I mean, you have coverage, but it's extremely pessimistic. If you pick gamma larger than 1, then turns out what happens is that you have no coverage, is useless. That corresponds to a choice of delta that is very big, and so you can see it from this confidence region. And if you have delta equal to gamma equal to 1 and delta equal to eta divided by n, then this converges to a well-defined non-degenerate limit. And then you can compute eta such that you can have coverage exactly equal to 1 minus alpha. All right. So what is this set? lambda of capital lambda of eta. This set is the following. So we define this convex function. So this convex function is 1/4 of the expected value of the dual norm. So so remember that I'm picking, no, it's not a dual norm just yet. So that's x minus y norm p squared. So what I do is I look at this object, this convex function. I define its dual, and this c, remember that this was the expected value of the Hessian of L. So I have, this is the set. Is the convex dual of this function composed with this matrix C, and I'm looking at this level curve in particular. So this is increasing, well, not surprisingly, but it's very nicely characterized. Okay, so what I can do now is compute, look at the coverage question. 0 is in this set. Well, if and only if phi star of C of negative Z0 would be here, because it has a positive sign, but C0 is equal in distribution to negative Z0. So because you have the C here. So this question is the same as asking, if this, finding the quantile, the 1 minus alpha quantile of this random variable, phi star of C0. And so this will have a well-defined quantile. You can now choose that quantile, and that leads to an optimal choice. In practice, this you can have plug-in estimators. So you can replace this by the empirical version. You can replace beta star by any consistent estimator, and under the assumptions I have by continuity, the choice is going to be asymptotically optimal. So you don't need to use cross validation. You don't need to use anything like that. You can use plug-in estimators and obtain an asymptotically optimal choice that is equivalent to solving this problem exactly. Okay, so this eta is the choice that I have in mind when I talk about these results. Now I'm heading to the last part of the talk, and what I want is to give a sense of where this stuff all come from. Before I do that, sorry, I mean the geometry of the confidence region. This is, so we can compute this object using the support function. This object is a little challenging to compute in high dimensions, but to compute the optimal delta, you don't need to compute this object. Okay, that's important. You just need to compute the quantile of this, and this can be used using plug-in estimation. So that's, but I'm interested in the geometry. Like I think, I want to understand how the geometry looks like. So if we look at different choices of P, for example, you go from something that kind of looks like this, not surprisingly, right, to something that as you increase P, it starts looking like that, right? So this is for P equals to 1. And you start from, larger P, it starts to kind of like becoming the geometry of the L infinity distance. And you have a lot of stuff in the middle. You see, this is the true parameter. This is the empirical risk minimization estimator. This one is the DRO estimator. So you have this hierarchy of different contours. This is the one that this is the ellipsoid of the empirical risk minimization estimator, corresponding to the smallest volume ellipsoid, right? So the maximum likelihood. So the smallest volume ellipsoid using the empirical risk minimization. You can see that this Wasserstein confidence region tend to have more volume. And you might ask the question, so why do I care then? Well, the point is that you might care because you might want to protect, that's the point, like the out of sample in certain directions. That's one thing. Like, so to the extent that you want, that you think that Wasserstein DRO makes sense, is interesting. You also would like to have a confidence region that contains the Wasserstein DRO estimator, and this one, the CLT one, might not contain it. And second, you can replicate the CLT one by choosing a Mahalanobis metric. So it would work the same. You can, if you keep insisting that, and you want to also enjoy the properties of DRO estimation, that's okay. You can preserve it and change your metric a little bit, and now have also this out of sample protection. So it you don't lose generality, and you gain rich interpretation. So it has the desired coverage. It contains both the ERM solution, and you can, as I said, you can choose a metric of this form that recovers the standard CLT confidence region. So one thing, this fact is actually non-obvious. This actually, to prove that this object belongs to this confidence region, actually you need to prove this duality result, and this duality result is non-obvious. And the thing that makes it non-obvious turns out to be this set is convex, of course, and this set is compact if you use the weak topology, but then this function is not upper semi-continuous in that topology. So that is kind of the problem. All right, I'm not going to talk about that, but this is kind of like a nice result. So this is what you can see. The CLT confidence region, doesn't cover the DRO confidence region. In terms of coverage, they of course are similar because they are designed to be to have the right amount of coverage. So where does this come from? Well, it comes from this. So something that is not hard to, is not hard to convince yourself. Like if you remember, this delta Pn is the space of beta P, so the arc mean, such that dP Pn is less or equal to delta. So this equivalent is almost immediate if this infimum here is attained, right? If this is inside here, then there is one minimized, and this is equal to 0 here. This is the condition for optimality. So if you have one decision that is in this set, well, then that means that there was one P for which this equation was equal to 0, and therefore the distance from Pn to all of the measures that make this equation equal to 0 has to be less than delta, because there is one here, right? And if this is equal to delta and the infimum is attained, then clearly you have one member here, right? So for that particular beta. So this is kind of like rewriting that, provided this is attained. Unfortunately, this is not attained always. So you need to take the closure to make this work, but it's attained typically. Okay, so I'm going to carry on assuming it's attained because it's typically the case that happens. So once you choose delta in this form, then the intuition is that, okay, so now you have chosen optimally, so therefore the fluctuations have to be of order 1/√10. So what you can do is you can define this random field around beta star, right center, of order 1/√10. And then you are cooking, right? At this point, it's just about, as I say, technique, right? Proving convergence of these, for example, uniformly on compact sets to get the convergence to the lambda delta, for example, object that we want. So I'm not going to do that. I'm going to fix U. I'm going to make U equal to 0 so that you can see where this happens. And I'm going to, get rid of that technical stuff of the U. And just kind of have fun, right? Just kind of have a heuristic derivation that you can quickly see that you can turn into a proof, and you can see everything, right? So I'm going to, so once beta star is fixed, right? Since u is equal to 0, I'm not going to carry this notation here. I'm just going to kind of like call this object H, because I want you to see just the scalings and the interpretation of them. Now this Rn is a linear programming problem, right? So this is this comes from an LP. This is a linear constraint. So this is an LP, and it has a dual, and so you can apply duality, and it's an infinite dimensional one, so it's not obvious, but you can do it, and you get this is the dual problem. Now you can start guessing the scalings, right? So delta, since you have finitely many constraints, the optimal transporter should transport locally of order 1 over root n, right? Because the fluctuations, you know, when you look at the empirical measure, the empirical version of this equation here, this is not going to be 0, but the error is going to be of order 1 over root n. So if I shift each of these outcomes by an amount 1 over root n, I can match I can make the equation to be satisfied. And now you look at how you know, how Rn should be scaled. As I told you, like this Rn, this is almost the Wasserstein distance of order 2. This, to make it a distance, you need to take 1/2. That makes it the Wasserstein distance of order 2. So therefore, this Rn should scale like 1 over n, because the distance, we're at the distance 1 over root n of the object. So the Rn scales like 1 over n. And then finally, you can say, okay, what is this Xi? Well, that's the sensitivity with respect to a change in the constraints. So how much the objective function changes when I change the constraints? Well, if I change the constraint by an amount 1 over root n, then I'm going to be matching, right? I can make this Rn equal to 0, and that means I would move the value of Rn by an amount that is 1 over n. So that means, you know, this is the ratio, that's the sensitivity, and so it should scale like n to the minus 1/2. So once I have this, then it's very easy. I'm just going to plug it in. I have, I substitute this lambda, right, by lambda to the 1/2. And then what I do is, this is now very nice. This calls for kind of adding and subtracting so that you can see a gradient sort of like pop up here. This is crying to you, take derivative of me. You take the derivative. You take the derivative. You have this already centered object under the null hypothesis, and that's it. So you have something here that is, this portion here is going to converge to, once you have the substitution, to the normal distribution. This is going to converge to Z0. And this object should give rise to this phi function of psi. So now this is something, this is a calculation we can do in closed form. Yes, so we do this, so this would converge to this, right? After a lot of technique, because this is not a compact set, so that requires a lot of work, but it's very plausible that you are going to have convergence of this part here to the normal. And so this is your function psi. So a little bit of massaging of this function then indeed gets you psi. So that's how it arises. I am going to quickly explain how this other part arises. Now once you have the delta, once you have the choice of eta doing this, as I said, you know, you have this phi star function, then you can talk about how to obtain asymptotic normality for this estimator. I'm going to also do it heuristically and just guessing the scalings, and the rest is just you know, technique. So the scaling again is similar for very similar reasons. The same type of argument of of sensitivity analysis this time tells you that lambda should be scaling like lambda times n to the 1/2. I use this duality result here from a paper in 2000. It was this is 2016, but it appeared 2019 in Math of OR. So once you have this duality result, again, this is an LP. That's where the duality comes from. Then you can do the same. Have the scalings here, plug it in, and you will take the derivative. This is going to be an inner product, which again you can solve in closed form, and you obtain an object that looks like this time. So this, by the way, shows that distributionally robust optimization is basically the same as regularization with sensitivity of the gradient. So there is a paper by Shichen and Rui Gao that has this equivalence. The big difference between what the result we get and their result is we have to do it in the parameter space. This is non-rigorous because you have to show that the approximation is uniform in beta, which they just do it pointwise. And then for this is the difference. So you can do it. And so what you can do is you have these insights of kind of showing we show that there is a Nash equilibrium, if you remember this duality. So you can actually get what's the structure of the Nash equilibrium that would correspond to solving this delta using the parallel condition once you expand this. And once you have this form, right, basically you end up with a form which is the empirical risk minimization estimator plus 1/√n and a well-identified here function v of beta. Well, then you are in business, right? So if you look at an M estimator of this form, then this is just this becomes easier. Out of this, just a Taylor expansion will tell you that the DRO solution is the same as the empirical risk minimization solution and a correction term, which is given by this plus an error that is asymptotically negligible. So the function is the function we derived before, and then you obtain this limiting result. So that's kind of the intuition. I'm going to finish with the conclusion, right? So what we did is we talk about an optimal theory for choosing uncertainty states in Wasserstein DRO, asymptotic normality of these DRO results, existence of Nash equilibriums, the structure of Nash equilibriums, and something that was hidden, and that will be the topic of another talk, is this very interesting object, which is projection. So you give me a Wasserstein, you give me an empirical measure, and you give me a linear manifold. In this case, was the manifold of probabilities that satisfy this constraint. And what I did was I projected that, and I obtained this limiting result. So there is a paper that will appear soon that talks about these types of problems, these projections, that can be used to beat the curse of dimensionality. So that's what I want to conclude with. That was what I brought to the table. I'm ready to answer questions if there are any.
Thank you very much for the nice presentation. Are there any questions? Please unmute yourself. And I can start maybe with the first question. Can you comment on the computational aspects of this estimator?
Yes, very good. This is an excellent question. Let me go back to my so computational aspects. Yes. So the majority of the results that exist that for this problem are reformulations, tractable reformulations. Okay, kind of making this using this duality result that I presented, and kind of having a form of the result. There is a paper that I wrote with Karthik Murthy and Fan Zhang. So this is 2018. That is called the Wasserstein DRO estimators, iterative algorithms and the structure. So so two things. Like first, in general, the results are you know, either you find explicit representations like, you know, group lasso, and or you can find a closed form solution. For example, when L of a beta transpose X, for example, is Lipschitz or convex and Lipschitz, and you use the Wasserstein distance of order 1, then you can, this is exactly the same as regularization. In the context of convex regression, you can, you know, you basically, there are two cases. Either you solve for the inner max, or if you don't solve for the inner max, the only result I know is when your function takes this form, when you look at affine policies, then there is a stochastic gradient descent algorithm. This problem turns out to be convex. So you have beta and lambda positive, and you have lambda delta plus expected value of Pn, and you have max of delta L, beta transpose X plus beta transpose delta minus lambda norm of delta P squared. In this case, this problem turns out to be strongly convex if L is just convex and twice differentiable in both beta and lambda. So you can apply stochastic gradient descent. And this inner optimization turns out you can solve efficiently in linear in the sense of optimization complexity. So the whole computational cost is very comparable to just solving, doing empirical risk minimization. So either you can solve the inner max explicitly, or in the case of affine policies, you can do it the same as if you have delta equal to 0. Those are the two cases. Most of the literature just simply recast this problem in a formulation you can put into a solver like MOSEC or something like that. So this is an excellent question. This is yes.
Other questions? Maybe another question. Can you get finite sample rates, or are you?
No. Yes, you can get this finite sample guarantees on the assumptions that are way stronger than what I'm assuming. So you need to have, for example, you know, sub-Gaussian tails or bounded random variables and things like that. And yes, I mean, Rui Gao has a nice paper recently from like a month ago where he gets finite sample guarantee for the value, not the optimizer, by the way, that's different. For the value function, for the generalization error, that type of finite sample guarantees with the 1 over root n, perhaps like some log, maybe a little bit of you know, deterioration, but you can get that in that context.
Thank you. Other questions? If not, I think it's 12:05. Let's thank Jose again for a nice talk. Virtual thanks, and I hope you have a good day. And thanks for everyone for joining. Thanks, Jose.
Thank you. Bye-bye.
Thank you. Bye.
Bye.